Hi, today we will discuss the different types of structural design patterns. Structural patterns are concerned with how classes and objects are composed to form larger structures. So, structural class patterns use inheritance to compose interfaces or implementations. So, there are different types of structural design patterns like adapter, composite, proxy, flyweight, facade, bridge, and decorator. So, we will discuss this in detail. Adapter. So, this convert the interface of a class into another interface that clients expect. So, adapter lets classes work together that couldn't otherwise because of incompatible interfaces. So it is also called as a wrapper, and we can use the adapter pattern when you want to use an existing class and its interface does not match the one you need, or you want to create a reusable class that cooperates with unrelated or unforeseen classes, that is classes that don't necessarily have compatible interfaces. And object adapter only, that is you need to use several existing subclasses, but it's impractical to adapt their interface by subclassing everyone. So an object adapter can adapt the interface of its parent class. So the participants are: first is target. This defines the domain specific interface that client uses. Client collaborates with objects conforming to the target interface. Adaptee defines an existing interface that needs adapting, and adapter adapts the interface of adaptee to the target interface. So a class adapter uses multiple inheritance to adapt one interface to another. An object adapter relies on object composition. So in this type, clients call operations on an adapter instance. In turn, the adapter calls adaptee operations that carry out the request. Although the implementation of adapter is usually straightforward, so there are some issues to keep in mind. So first is implementing class adapters in C++. So in a C++ implementation of a class adapter, adapter would inherit publicly from target and privately from adaptee. Thus, adapter would be a subtype of target but not of adaptee. Then pluggable adapters. So there are three ways to implement pluggable adapters. The first step uh, is common to all three of the implementations. It is to find a narrow interface for adaptee, that is the smallest subset of operations. So a narrow interface consists of only a couple of operations. They are easier to adapt than an interface. The narrow interface leads to three implementation approaches. First is using abstract operations. So this defines corresponding abstract operations for the narrow adaptive interface. Then using delegate objects. So in this approach, a delegate object can be accessed using the hierarchical structure, and then so the next type is bridge. Bridge decouples an abstraction from its implementation so that the two can vary independently. It is also known as handle or body. So you can use the bridge pattern when you want to avoid a permanent binding between an abstraction and its implementation, or both the abstractions and their implementations should be extensible by subclassing. or changes in the implementation of an abstraction should have no impact on clients. That is, their code should not have to be recompiled. And you want to hide the implementation of an abstraction completely from clients, or you have a proliferation of classes. Such a class hierarchy indicates the need for splitting an object into two parts. Or you want to share an implementation among multiple objects, and this fact should be hidden from the client. So the participants in bridge are abstraction. So this defines the abstraction's interface and maintains a reference to an object of type implementer. Then refined abstraction extends the interface defined by abstraction, and implementer defines the interface for implementation classes, and this interface doesn't have to correspond exactly to abstraction's interface. And it typically the implementer interface provides only primitive operations, and abstraction defines higher level operations. The concrete implementer implements the implement or interface and define concrete implementation. So the consequences are decoupling interface and implementation. So an implementation is not bound permanently to an interface. The implementation of an abstraction can be configured at runtime. It's even possible for an object to change the implementation at runtime. And decoupling abstraction and implementer also eliminates compile time dependencies. And changing an implementation class does not require recompiling. The property is essential when you must ensure binary compatibility. And decoupling also encourages layering that can lead to a better structured system. And improved extensibility. You can extend the abstraction and implementer hierarchies independently. And hiding implementation details from clients. So you can shield clients from implementation details like sharing of implementer objects and the accompanying reference count mechanisms. So implementation. So we have to consider the implementation issues when applying bridge pattern. So only one implementer. So in situations where there is only one implementation, creating an abstract implementer class is not necessary. This is a degenerate case of bridge pattern. There is a one-to-one relationship between abstraction and implementer. So creating the right implementer object. If abstraction knows about all concrete implementer classes, then it can instantiate one of them in its constructor, and it can decide between them based on the parameters passed to its constructor. Another approach is to choose a default implementation initially and then change it later according to usage. It is also possible to delegate the decision to another object altogether. And then the third one is sharing implementers. So we can share implementations among several objects. The body stores a reference count that the handle class increments and decrements. Then using multiple inheritance, we can use multiple inheritance in C++ to combine an interface with its implementation. Next type is composite. So this type composes objects into tree structures to represent part-whole hierarchies. So composite lets clients treat individual objects and compositions of objects uniformly. So the key to the composite pattern is an abstract class that represents both primitives and their containers. So you can use the composite pattern when you want to represent part-whole hierarchies of objects and you want clients to be able to ignore the difference between compositions of objects and individual objects. So clients will treat all objects in the composite structure uniformly. So the participants are component. It declares the interface for objects in the composition and also implements default behavior for the interface. And it also declares an interface for accessing and managing its child components. Then leaf represents leaf objects in the composition. A leaf has no children and it defines behavior for primitive objects in the composition. And composite defines behavior for components having children. It stores child components and implements child-related operations. The client manipulates objects in the composition through the component interface. So clients use component class interface to interact with objects in the composite structure. If the recipient is a leaf, then the request is handled directly. If the recipient is a composite, then it usually forwards requests to its child components and performs additional operations before and or after forwarding. The composite pattern defines class hierarchies consisting of primitive objects and composite objects. Primitive objects can be composed into more complex objects, which in turn can be composed and so on recursively. So wherever client code expects a primitive object, it can also take a composite object. And it also makes the client simple. So clients can treat composite structures and individual objects uniformly, and clients normally don't know whether they are dealing with a leaf of a composite component. So this simplifies client code, and because it avoids having to write tag and case statement style functions, and it also makes it easier to add new kinds of components, and newly defined composite or leaf subclasses work automatically and clients don't have to be changed for new classes. And it also make your design overly general. The disadvantage of making it easy to add new components is that it makes it harder to restrict the components of a composite. So there are many issues to consider when implementing the composite pattern. So first is explicit parent references. Maintaining references from child components to their parent can simplify the traversal and management, but the parent reference simplifies moving up the structure and deleting a component. And also parent references help support the chain of responsibility pattern. And it's often useful to share components, for example, to reduce storage requirements. But when a component can have no more than one parent, sharing components become difficult. And one of the goals of the composite pattern is to make clients unaware of the specific leaf or composite classes they are using. So to attain this, component class should define as many common operations, and the component class usually provides default implementations for these operations. Then declaring the child management operations. So we can add and remove operations for managing children. This is an important issue in which classes declare these operations in the hierarchy. So the decision involves a trade-off between safety and transparency. So defining the child management interface at the root of the class hierarchy gives you transparency, and it costs safety also because clients may try to do meaningless things like add or remove objects from leaves. And defining child management in the composite class gives safety because any attempt to add or remove objects from leaves will be caught at compile time. And but we lose transparency because leaves and composites have different interfaces. And you can be tempted to define the set of children as an instance variable, but putting the child pointer in the base class incurs a space penalty even though leaf never has children. So this is worked only if there are relatively few children in the structure. And we can also order the children. Many designs specify an order on the children of composite. So when child ordering is an issue, we can design child access and management interfaces carefully to manage the sequence of children. And if you need to traverse or search compositions frequently, then cache traversal or search information about its children can be implemented. And in languages without garbage collection, it's usually best to make a composite responsible for deleting its children when it's destroyed. An exception to this rule is when leaf objects are immutable and thus can be shared. So composites may use a variety of data structures to store their children, including linked list, trees, arrays, and hash tables. The choice of data structure depends on efficiency. So the next type is decorator. This attach additional responsibilities to an object dynamically, and decorators provide a flexible alternative to subclassing for extending functionality. It is also known as wrapper, and we can use decorator to add responsibilities to individual objects dynamically and transparently, that is without affecting other objects, and for responsibilities that can be withdrawn and when extension by subclassing is impractical. So sometimes a large number of independent extensions are possible and would produce an explosion of subclasses. So, or a class definition may be hidden or otherwise unavailable for subclassing. So the participants are component. It defines the interface for objects, and concrete component defines an object to which additional responsibilities can be attached. Decorator maintains a reference to a component object and also defines an interface. Concrete decorator adds responsibilities to the component. So decorator forwards request to its component object. It may optionally perform additional operations before and after forwarding the request. So decorator pattern has two key benefits and two liabilities. So more flexibility than static inheritance. That is, the decorator pattern provides a more flexible way to add responsibilities to objects that can be had with static inheritance or multiple inheritance. And decorator offers a pay-as-you-go approach to add responsibilities. Instead of trying to support all features in a complex class, you can define a simple class and add functionality incrementally with decorator objects. And a decorator acts as a transparent enclosure. But from an object identity point of view, a decorated component is not identical to the component itself, but we should not rely on object identity when you use decorators. And a design that uses decorator often results in systems composed of lots of little objects that looks alike. The objects differ only in the way they are interconnected, but not in their class or in the value of the variables. So there are issues that can be considered when applying the decorator pattern. So a decorator object's interface must conform to the interface of the component it decorates. So concrete decorator classes must therefore inherit from a common class. And there is no need to define an abstract decorator class when you only need to add one responsibility. So in that case, if you're dealing with an existing class hierarchy, uh, you can merge decorator's responsibility for forwarding requests to the component into the concrete decorator. And to ensure a conforming interface, components and decorators must descend from a common component class, and it's important to keep this common class lightweight. That is, it should focus on defining an interface, not on storing data. And we can think of a decorator as a skin over an object that changes its behavior. An alternative is to change the object's guts. That is, the strategy pattern is a good example of pattern for changing the guts. Next type is facade. So this provides a unified interface to a set of interfaces in a subsystem, and facade defines a higher level interface that makes the subsystem easier to use. And we can use facade pattern when you want to provide a simple interface to a complex subsystem, or there are many dependencies between clients and the implementation classes of an abstraction, or if you want to layer your subsystems. So the participants are facade. This knows which subsystem classes are responsible for a request, and it also delegates client request. And subclass systems implement subsystem functionality. It handles work assigned by the facade object, but it have no knowledge of the facade, that is, they keep no references to it. The clients communicate with the subsystem by sending requests to facade. It forwards them to the appropriate subsystem objects, and the subsystem objects perform the actual work. The facade may have to do work of its own to translate its interface to the subsystem interfaces, and clients that use the facade don't have to access its subsystem objects directly. So the consequences are the facade pattern offers these benefits, like it shields clients from subsystem components, so reducing the number of objects that clients deal with and making the subsystem easier to use. And it promotes weak coupling between subsystem and its clients. And it does not prevent applications from using subsystem classes if they need to. Thus, you can choose between ease of use and generality, and it also keeps flexibility. And we have to consider these issues when implementing a package. So the coupling between clients and subsystem can be reduced by making facade an abstract class. So then clients can communicate with subsystem through the interface, and this coupling keeps clients from knowing which implementation is used. An alternative to subclassing is to configure a facade object with different subsystem objects, and to customize this, we can simply replace one or more of its subsystem objects. And a subsystem is analogous to a class in both that both have interfaces and both can encapsulate. So it's useful to think of a public and private interface of a class. So public interface consists of classes that all clients can access, and the private interface is just for subsystem extenders. So next type is flyweight. So this use sharing to support large numbers of fine-grained objects efficiently. A flyweight is a shared object that can be used in multiple contexts simultaneously. So this acts as an independent object in each context. That is, it's indistinguishable from an instance of the object that is not shared. And flyweights cannot make assumptions about the context in which they operate. The key concept here is the distinction between intrinsic and extrinsic state. So intrinsic state is stored in the flyweight. It consists of information that is independent of the flyweight's context. So it is shareable. Extrinsic state depends on and varies with flyweight's context, and therefore it cannot be shared. And client objects are responsible for passing extrinsic state to the flyweight when it needs. So flyweight model concepts or entities that are normally too plentiful to represent with objects. So For example, a document editor can create a flyweight for each letter of the alphabet. Each flyweight stores a character code, but its coordinate position in the document can be determined from the text layout algorithms and formatting commands. So the character code is intrinsic state, while the other information is extrinsic. The flyweight pattern's effectiveness depends heavily on how and where it is used. So apply the flyweight pattern when all of the following are true. That is, an application uses a large number of objects. Storage costs are high because of the quantity of objects. Most object state can be made extrinsic, or many groups of objects may be replaced by relatively few shared objects once extrinsic state is removed, and the application does not depend on object identity. So the participants of flyweight are: flyweight declares an interface through which flyweights can receive and act on extrinsic state. Then concrete flyweight implements the flyweight interface, and it also adds storage for intrinsic state. A concrete flyweight object must be shareable, and any state it stores must be intrinsic, that is, it must be independent of the context. And unshared concrete flyweight, not all flyweight subclasses need to be shared. The flyweight interface enables sharing. It does not enforce it, and it's common for unshared concrete objects to have concrete flyweight objects as children at some level in the flyweight object structure. And flyweight factory creates and manages flyweight objects. When a client uh, requests a flyweight, then it ensures the flyweights are shared properly, and it also supplies an existing instance and creates one if none exist. And client maintains a reference to flyweights, and it also computes or stores the extrinsic state of flyweights. So this states that the state that a flyweight needs to function must be characterized as either intrinsic or extrinsic. Intrinsic state is stored in the concrete flyweight object. Extrinsic state is stored or computed by client objects. Clients pass this state to the flyweight when they invoke operations. Clients should not instantiate concrete flyweights directly. Clients must obtain concrete flyweight objects from the factory object to ensure they are shared properly. So flyweights may introduce runtime cost uh, associated with transferring, finding, or computing the states. So such costs are offset by space savings. It can increase as more flyweights are shared. So storage savings are a function of several factors like the reduction in the total number of instances, the amount of intrinsic states, whether extrinsic state is computed or stored. So the more flyweights are shared, the greater the storage savings. The savings increase with the amount of shared state, and the greatest savings occur when the objects use substantial quantities of intrinsic and extrinsic state, and extrinsic state can be computed. uh, it cannot be stored. Then we can save on storage in two ways. That is, sharing reduces the cost of intrinsic state, and we can trade extrinsic state for computation time. And flyweight pattern can be combined with the composite pattern to represent hierarchical structures like a graph with shared leaf nodes. And a consequence of sharing is that flyweight leaf nodes cannot store a pointer to the parent. So parent pointers can be passed to the flyweight as part of the extrinsic state. So this has a major impact on how the objects in the hierarchy communicate with each other. So we have to consider these issues when implementing the flyweight pattern. The pattern's applicability is determined largely by how easy it is to identify extrinsic state and remove it from shared objects. So removing extrinsic state uh, help to reduce storage cost if there are many different kinds of states. So extrinsic states can be computed from a separate object structure. And managing shared objects, because objects are shared, clients should not instantiate them directly. So shareability implies some form of reference counting or garbage collection. So next type is proxy. This provides a surrogate or placeholder for another object to control access to it. It is also called surrogate. So proxy is applicable whenever there is a need for a more versatile reference to an object than a simple pointer. So these are some common situations in which proxy pattern is applicable. So first is a remote proxy, which provides a local representative for an object in a different address space. A virtual proxy creates expensive objects on demand. Protection proxy controls access to the original object. Protection proxies are useful when objects should have different access rights. And a smart reference is a replacement for a bare pointer that performs additional actions when an object is accessed, like counting the number of references, or loading a persistent object into memory, or checking that the real object is locked, like that. So the participants are proxy. This maintains a reference that lets the proxy access the real subject, and proxy may refer to a subject if the real subject and subject interface are the same. And it also provides an interface, and it also controls access to the real subject and responsible for creating and deleting it. So other responsibilities depends on the kind of proxy. That is, remote proxies are responsible for encoding a request and its arguments and sending the request. Virtual proxies may cache additional informations and and it can postpone accessing it. And protection proxies check that the caller has the access permissions. And subject defines the common interface so that a proxy can be used anywhere a real subject is expected. And the real subject defines the real object that the proxy represents. So proxy forwards request to the real subject when appropriate, depending on the kind of proxy. So the consequences are the proxy pattern introduces a level of indirection when accessing an object. The additional indirections has many uses depending on the kind of proxy. So a remote proxy can hide the fact that an object resides in a different address space, and a virtual proxy can perform optimizations like creating an object on demand. And both protection proxies and smart references allow additional housekeeping tasks when an object is accessed. There is another optimization that proxy pattern can hide from the client. It is called copy on write. It is related to creation on demand. Copying a large and complicated object can be expensive. So if the copy is never modified, then there is no need to incur this cost. By using a proxy to postpone the copying process, we can ensure that we can pay the price of copying the object only if it is modified. The proxy pattern can exploit the following language features, like overloading the member access operator in C++. That is, C++ supports overloading operator. the member access operator. So overloading this operator lets you perform additional work whenever an object is dereferenced. So this can be helpful for implementing some kinds of proxy. The proxy behaves just like a pointer. And Smalltalk provides a hook that you can use to support automatic forwarding of request. So Smalltalk calls does not understand. In Smalltalk, uh, this is a message when a client sends a message to a receiver that has no corresponding method. So proxy class can redefine this so that the message is forwarded to its subject. Proxy does not always have to know the type of real subject. If a proxy class can deal with its subject, then there is no need to make a proxy class. The proxy can deal with all real subject classes uniformly. So another implementation issue involves how to refer to the subject before it is instantiated. Some proxies have to refer to their subject whether it is on disk or in memory. That means they must use some form of address space independent object identifiers. So we can use the file name for this purpose.